see if we can get. So, welcome to this software architecture class 2018. My name is Jesper, and I'm the teacher responsible for this course. I believe I will manage everything, so I will grade your assignments, grade your homework, whatever. So we are live streaming this this lecture and all lectures. We managed to get the technology working with us today. If you have any questions, you can, and for the distance learning students, if you have any questions, you can write them in the chat window in YouTube, and then one of the students here in the room will relay the questions to me, and I will answer them. So first, I believe that you can all hear me and see me. Now, we'll see if I can go into, see if I can get the screen there. Looks like it. So, software architecture is a theme that has been around in software development for, well, something like 30 years or so. The background is actually that systems grew and became bigger and bigger. And at some point, they were just too big for a small group of people to develop them. And that meant that you needed to throw in more people into your projects. And suddenly, you hit this magic threshold where you couldn't really rely on standard ways of communicating. So direct communication or passing around papers. You needed to divide the work up into chunks that sub-teams or subgroups in this larger teams could work on independently to some extent. So this is the background. We see complex systems. These systems are invisible. At least there is no single individual that can comprehend the entire system. It's like a shared thing that we need the knowledge of many people to be able to develop these kinds of systems. And that means that system design becomes a group activity. And suddenly, we need to align work. Because we want to decentralize, divide this big system up into subsystems where teams can work independently on the subsystems. And we should do this in a way that we preserve the integrity of the system. That means that when these parts have been developed independently and we put them back together, the whole should work. It's not a big challenge to divide work up, have all these groups work on solving some subproblems, but then when you put the big thing together with the pieces, that's the great challenge. So what we will try to do in this class is to show you some proven ways of how to address this or these kinds of decisions. Because it's all about design decisions. During development, we will face design decisions on the level of should I use this sorting algorithm or should I use that data type? How should I represent this? What would be should be the signature of this method, etc. Those decisions doesn't necessarily have a very big impact on the whole system. Those are examples of very local design decisions. But if we would like to divide work up in a group among the individuals in a group of people, how should we do that? Well, first, we need to agree as a group on things that we all depend upon. Before we branch out, we should agree on the things that we all depend upon. So what does that mean when we talk about software? A data type? Nah, that's a local one. But if we say that we're gonna use this protocol stack for communication, that's something that could affect other teams, many teams. If we say that we will use this way or this approach for authenticating users, that's also something that has an effect on the entire system or a large part of the system. Those decisions are more like strategical decisions. We must make these decisions and communicate it to all the teams so that because these decisions are actually requirements on the teams when they work. Because if they don't stick to these strategic decisions, it will not work when we put it back together. So when we talk about requirements, when we talk about decisions, we usually think about functionality and quality. And what you will see in this class is that, well, they blend. Quality is also functionality. And some quality cannot be achieved if we don't add functionality to the system. Think about usability, for instance. What is it that makes this cell phone more usable than some other cell phone? Well, it's functionality in the user interface, probably. So in this class, we will look at these types of decisions and how to document these decisions and how to communicate them. Well, since, I would say always, decomposition has been the principal tool in our toolbox for dealing with complexity. If we have a complex problem, we start to look for smaller problems in that complex problem, divide it up into these subproblems, and then we try to address the subproblems. And we continue with this decomposition until we reach a problem that we can deal with. So, when it comes to functionality, you know how to program, I assume. What kind of mechanisms in programming languages do you know that we use to decompose complex problems? Any suggestions? Any ideas? Classes? Yes? Functions, methods? Sure? Those are, well, containers for subproblems. And then we can combine these by, well, calling them in an iterative way or using different control statements to steer the path the program follows. But if we think about a problem like Google Docs, think about Google Docs. Is the class a suitable metaphor or a suitable abstraction for a system of that size? Or do we need something else? Well, I think that people have come to the conclusion that we need something else. We need something at a higher level of abstraction in order to deal with these system-wide decisions. And that's the architecture level. So the idea now is to decompose our systems. That means finding the right subsystems, finding solutions to these subsystems, and put them back together. But as I said before, if we're not careful when we make the decisions here, we will end up in situations where pieces don't fit, for sure. And those mismatches can be simple to find, but they can also be extremely complex, difficult to find. So that's why it's worthwhile to make these decisions or spend some extra effort on the architectural decisions before you branch out. Because what we're striving for is system integrity, and it doesn't matter what type of qualities you have in your parts of the system if the system as a whole doesn't exhibit that property. You have failed. So that means that if you have a very super secure subsystem over here, well, if the system as a whole is not secure, it doesn't matter. So if you make decisions about security, those decisions must color the entire system, not just a single part. And here we see another statement. We cannot, with any guarantees at least, achieve this bottom up. We cannot have 10 people work on 10 different parts, put it together, and expect that to work. But if we make decisions before we branch out, it's more likely, as long as these sub-projects work together. So, let's see now how do you do this? Well, if you make these decisions, well, some parts of the system require this much of security, while others require, well, almost none. Should it make the entire system super secure? Well, could be. But it could also be that you have to trade one quality for another. So security, for instance, it comes with a cost. There's a cost in usability typically, because you have to log on to the system all the time, and there's also a cost when it comes to performance. So you need to trade one for the other. This is one example of decisions that you must make before you branch out. Because if one sub-team prioritizes performance and the other prioritizes security, they will not fit together when you bring the pieces back. So what you do then is that you make the decisions and you define design rules, actually, or rules that each sub-team should work accordingly to. And if they do that, it's more likely that it will fit when you integrate. So software architecture is actually all about this, coming up with the right decomposition. Then you leave it to the teams to do whatever they want to do within the boundaries you have defined at the architectural level. You focus on the system concerns, functionality and quality, and the trade-offs. You can see trade-offs also between functionality and quality. We need this function. However, it's just too costly when it comes to resources. So if we go for that piece of functionality, we need to sacrifice something else. Trade-off between functionality and quality. And what we would like to install with this class is actually some engineering principles for how to do this. And what you will see is that it's not really a big difference compared to what you should do when you design a system on the class level. The abstractions are different, but the ideas are similar. You have a design problem, you have different design alternatives, you analyze the design alternatives, and you go for the one that fits your target. Because engineering principles is another aspect on integrity. If you use these principles or practices, it will be more likely that the system will integrate well and work at the end. So here are some statements about architecture challenges. You need to deal with multiple concerns, multiple qualities. You need to share a vision within a team. And how to do that? Well, you will need some kind of language to express your architectures, your decisions, and you need some kind of support for the decision making. So, this is from an ISO standard, and I highlighted two elements here: stakeholder and concern. So why is that important? Well, this decomposition is about finding a decomposition for a system that deals with all concerns that system may have. Functionality, performance, security, deployability, etc., etc. And as an architect, it's your responsibility to describe how the system will deal with this concern. So why do I have this stakeholder guy in the middle? Well, the stakeholder guy here in the middle tells us that there will be different types of stakeholders. And it could well be that some stakeholders are just interested in some aspect of the system, while others are interested in the system on a more general level. It also indicates that some stakeholders are trained software engineers, others are not. So the challenge here is really about expressing how a system deals with a concern for a particular group of stakeholders. One quick example of that: we have functionality in a system. System functionality. How would you express to a top-level manager what functionality the new system he finances will have? How would you describe that? Yeah, some kind of document, sure. But something that you have picked up during the years here at the university. Yeah, something like requirements, sure, but can you say something more specific about what type of... Yeah, functional requirements. How do you model functional requirements? In a requirement document that could contain something. Some UML diagram, sure. Any idea for a specific type of UML diagram that could be very useful in this case when you have a top-tier manager? Yeah, one very specific UML model. Use cases could be one way to express this. However, if you want to communicate the requirements to a team of developers, use cases are not enough. You need more details. So this is one example where different stakeholders will require different types of descriptions or information regarding the concerns. And this means that we will have different views on a system. And these views are constructed in a way that you can construct a view for a stakeholder. So this stakeholder is this top-level manager now. The concern is functionality, and we create a view, put it simple, a use case model. Next view, same concern, functionality. Stakeholder now is designer, say. Okay, use cases is one part, but the view also contains sequence diagrams, something like that. Suddenly we have two views on the same concern for two different stakeholders. So the main message of this is actually that as an architect you will talk up and you will talk down the hierarchy, so to speak. So you need to master a little bit of business side, but also the technical side. Because some of these decisions are more concerned with business, and some decisions are technical. So you will sit somewhere in the middle as a middleman that mediates communication up and down. Okay, an example. I mentioned Google Docs before, and this is not Google Docs, it's more like Jesper Docs. But a small application where we share documents. You can start at this very abstract level, and you start to think about, what is important here? And what is important is typically requirements or concerns. So in this example, you have some functional requirements. That is that we should have a system that can share files. That's like a minimal requirement. If we don't do that, if we don't support that, well, no one will use it. But we also have some quality requirements. Performance, security, reliability, for instance. And those are, in my opinion, equally important. So even though we can share files, it doesn't matter that someone would like to use it, because if it's not secure, Who would like to share files with anyone? Well, maybe that could be the case. Or who would like to share files if it took like minutes to upload and minutes to download? And for this little system, we have a team of developers. And we have Peter, and we have Mary, and we have Paul. And Peter, he's our front-end guru. And Mary, she masters all projects, the back-end for our projects, while Paul is like a manager who likes to talk to customers. Paul now would like Peter and Mary to work independently on a client and a server side without too much daily coordination. I hope you understand that this is an oversimplification, but of course they could work together on this, but now we want two teams, so they want to work independently. So we need to make some decisions before they can go to their respective offices and work. And those decisions are architectural decisions. Because first we need to agree upon which functionality should be on the client side and which functionality should be on the server side. If Peter and Mary doesn't communicate about this before they branch out, we might end up with a client and a server that has overlapping functionality. So we need to allocate functional responsibilities to, in this case, the two subsystems we have, client or front-end and back-end. We also need to agree upon how to implement or how to achieve various qualities. For instance, security. In this case, security has two parts. We need to make sure that the client side is secure and the server side is secure, and also, of course, the communication in between. And that's an example of something that cannot be managed independently. There must be some system-wide agreement. So we come back to this standard, and you can see that it's more to it than just the stakeholder concern and view. But the stakeholder in this case, say that we have functionality, we have our developers, Peter and Mary, they are the same in this case. And the concern here is also the same. The system or the allocation of functionality in the system. And for that, we could have the same view. But let's look a little bit more to the stakeholder and concerns here. So this slide tells us a little bit more. This is more, well, text directly from the standard. So stakeholders of a system have concerns with respect to the system. So if you don't have a concern with respect to the system, you're not a stakeholder, period. Concerns arise throughout the life cycle. Okay, what does that mean? Well, it means that concerns could arise during deployment of a system. after a system has been put into production, new concerns may arise. So it's not something that we do up front. It's actually something that has to be dealt with continuously throughout the lifetime of a system. So we deal with these in views. And a view addresses one or more of the concerns. We come back to this next week too, but one view can address one or more concerns. It consists of models, and a model can be more or less, well, everything from a very formal model. Can have a formal performance model, for instance, down to a very informal boxes and lines drawn by hand on paper. So whatever is valuable can be part of a view here. If you look at the concerns, this is an extract from the standard. And as you see, there is an abundance of concerns, overlapping concerns. It's impossible to learn and enumerate and understand all these concerns, because it spans the range from business goals and strategies down to functionality, even down to resource utilization. There are so many different things. And this is also something that you see in architecture, because an architect needs to make decisions with respect to a concern. I'm not an expert in privacy. There are privacy experts who knows how to architect systems for privacy. I'm not a reliability guy either, but some architects are experts in that. So what you often see in big projects are teams of architects that together work on this decomposition, allocating responsibilities to the parts of the system, and that sees to that all these qualities together with the functionality is achievable or can be achieved. So let's go back to the example here. So we have a system where we should share files, we have some qualities, and picture yourself now, you're the architect. And I would like you to describe your decisions to me with respect to how you have decomposed the system and how you have allocated functionality or responsibilities to the various parts of the system. How would you do this? Well, you need to start somewhere. The only thing we know is that it will not be perfect. But you need to start somewhere and then improve iteratively. And this means that it can be, well, architecting can easily be combined with iterative and incremental development processes. However, it is a little bit more challenging. And one of the lectures will actually talk about how to deal with architecture in agile software development. Because that is indeed a challenge, because what is at the very heart of agile methodology? Well, that is that you should have this little team who self-organizes, who decides on certain things like what they should develop and how they should develop it. But if you have projects with hundreds of people and you still would like to have agile teams, how do you deal with that? Do you have like a team that sits for 2 months before the actual project starts and lay out the architecture? Doesn't work, because remember, we just said that these concerns arise during the entire life cycle. So as new functionality or functional requirements come in from your product manager, it might well be that the architecture does not address or does not help you, assist you with that. So you need to reconsider your architecture. But still, you need to start somewhere. And the first level decomposition is the place to start. So, the first level decomposition is a very simple view where you identify the key subsystems in your system and allocate responsibilities. And you can start with the core functionality here. When you've done that, you also need to know which subsystems communicate with which other subsystem. And they do that by providing services to others or requiring services from others. And this is something you can sketch easily on a whiteboard. Or you can use some fancy UML notation for it. There's no value in the notation besides that you don't need to discuss what that box and what that arrow means. That's defined by the language. But besides that, boxes and lines are fine. So let's see if this one works. You remember this sharing the files? Yeah? Subsystems. What do we need? Any ideas for subsystems? Can you see that on the screen? Should probably have a black pencil next time. It's hard to see? Okay. That one better? Or is it the working black? Just throw it. Thank you. Ah, that one should work. Okay. So, now you're the architect. You seen matrix? You're the architect, okay? You want to share files. Which subsystems do you see? Yep. Is that a subsystem? Storage?
Syncing network, like user interface, something like a website or
Some client somewhere. Yeah. we can make this really simple. We can do it like this, because this one always works. And now we have some responsibilities. We had like upload files. Well, that's definitely something here. But probably over here on the client side as well. Then you have download, you have sharing, you have users. You need users too. And you continue like this, on and on and on, until you have like populated the main components with responsibilities. Don't go into too many details. Remember, it's like a first level. Not second or fifth, it's the first level. What else do we need? We need some interfaces, because the client here probably requires an upload service, and this server requires some kind of storage, and this one provides an upload service. So what you do is integrity. Because if this one requires something that this one provides, if you put them together, that should be doable, because this guy here provides something that this guy requires. And you agree upon the protocol, you agree upon the signatures, whatever, before you branch out and work independently. First level decomposition. Put it here. Okay. So what you saw now was an example of a, well, very naive brainstorming approach, and of course that's typically where we start, but at some point we need to address the problems here a little bit more systematically. Because if we would like to achieve this integrity in the system, we cannot, well, continue in this style. We need to do it a little bit more strict. So if you look at the functionality, identify subsystems, assign responsibilities, sure. Identify the subsystem interfaces, that's fine, no problem. But when it comes to quality, the problem changes a little slightly. The nature of the problem is different. Because quality we can achieve quality in two different ways. We can achieve it by structure, and we can achieve it by behavior, or the combination. So here we talk about architectural mechanisms. And these mechanisms may add subsystems and functionality to the first level decomposition. Let's go back to this one here. What do I mean by that? Well, let's talk about security. Okay? How can we, well, security is this broad. But let's say that we want to make sure that we have at least keep track of our users. So how can we do that? Authentication, yes. How many different types of authentication do you know of? More than one? Three? I would say it's probably like 3 popular ones. That's typically what you see. But then there are more historical ones and new ones that you didn't know of or couldn't imagine. But for the security concern here, we have a couple of options. One could be that over here we have some kind of user management. Now it's no longer first level, by the way. Now we add a subsystem with responsibilities down here. But if we would like to use this for authentication, well, we need to make use of that in the system. Here, probably. Here. And here. And if you use a homebrew solution here, well, you need to invest a lot of time. But you can also start to reason at this level about reuse, reusing existing systems, reusing services. You can have like you could imagine to have a Facebook authentication here. Why, I don't know, but it's just an example. And when we have more than one concern, reasoning about these trade-offs becomes important. Because if we can't find the right balance between these concerns, we will not have happy customers at the end, or happy stakeholders, I should say, not just customers. So what you see is that people have developed reasoning frameworks, and that sounds really advanced, but what it is really ways of expressing knowledge about how to do things and how to evaluate candidates. With that, you have a reasoning framework. And this is like a core component for you when you start to decompose and allocate responsibilities. Because from some point, you have to make sure that the system is secure, but then you need to make sure that the security aspect doesn't consume too many resources so that it drags down the performance or affects the usability too much. So architectural mechanisms are cross-cutting the system, like the security example we had over on the whiteboard. Which makes it much more challenging, because cross-cutting means that we put integrity at risk. Here's our client-server example, just to illustrate this. We have a number of clients on the left-hand side here, or your right, your left here, yes, and then we have the server on the right-hand side. Think about scalability. When it comes to client-server, systems, scalability is a challenge. Scalability is a concern. So why is it that scalability is a challenge for client-server systems? Well, that is that you have this central point, bottleneck, in the middle of your system. So what you can see here is that the client-server, the way we decided to decompose our system over on the whiteboard there, that's not optimal if scalability is one of the most important properties. What else do we have? Reliability. Single point of failure. Of course, we have a server. Reliability goes down. However, security is kind of easy here, because we have one single interface between the clients and the server. So we just need to make sure that that communication, that interface is secure. If we can do that, we have, well, a little bit oversimplification maybe, but we have secured the system. Are there any alternatives to this architecture? Peer-to-peer. So what is the difference between a client-server architecture and a peer-to-peer architecture? Well, that is that our peer-to-peer architectures, the elements there has a server and a client aspect. It's a little bit of both. So what kind of properties do we see here? Scalability. Suddenly, scalability is built into this structure. If we get a new client, we get a new server. Reliability goes up, because if a server goes down, the information can be found somewhere else on, well, some of the other servers. However, security, and now I just talk about implementation. At least in my book, it will be a little bit more challenging to secure the peer-to-peer compared to a client server. So what you see here is that you have, depending upon which structure you use for your decomposition, you amplify some concerns. You enable some of the concerns. Or you make it more challenging, inhibit some concerns. Again, the architect's role is to find the good enough balance here so that we can achieve the goals for the system. Second strategy for achieving quality in your system is, as we saw over on the security example, to add functionality. You add functionality to the system. In the architecture world, that's called tactics. It comes from the an organization that works tightly with the Department of Defense in the US, so that's why it's called tactics. You need to convince some generals that this is a good method. Let's call it tactics. So, availability. Availability is extremely important for a system like ours. And availability means that, well, the probability that the system is available to deliver services to its users at any point in time. So what can we do to guarantee availability? Well, we can do a lot. We can do many things. Remember our client-server solution? That client-server solution made it easier for us to implement security. However, it was challenging when it came to reliability, which is a threat to availability, and scalability, which is also a threat to availability. So we can, for instance, introduce a load balancer. Many times you get this from the software stacks you use, but not always. So sometimes you have to do it yourself. When it comes to failures, which affects reliability, you can recover from faults. But you're not an expert in fault recovery. And you cannot afford to hire an expert. So what do? Well, you go for the tactics, because the tactics gives you a direction. What do you need in terms of behavior, functionality in your system in order to achieve fault recovery, which will improve your reliability? And for that, you will you have to detect faults first. Here. How do you detect faults? Well, there are many different ways to detect faults. You can have, for silent node failures, you can use a ping echo. You can use a heartbeat. There are many different ways to detect that a node in your system has failed. And now you can pick one. Pick one that you feel comfortable with, or pick one that you believe satisfy your needs most. Next, preparation and repair. If you have detected a failure, you need to recover from it. Okay, so 2 steps: prepare and repair and reintroduce. That can be anything from flipping from one server to another if you have active redundancy. Then you don't hopefully need to repair. So the reintroduction here is that you have shadowed all the communication between this backup and the live server. You can have a spare, which actually means that you have a spare server that you switch on. So there are many ways to recover from and reintroduce a service to a system. Prevent faults are a little bit more challenging. If it's a hardware fault, I don't really see how you can do that. If it's a software fault, there are ways of doing it, but we don't need to talk about that here. So you see that the structure enables or inhibits, but we can add behavior, add functionality to the system to support various qualities. So this is actually what software architecture is all about. Functional allocation, and see to that your architecture supports quality. That you make all the decisions about allocation, about system-wide responsibilities before people start to work independently on the subsystems. Why do you do that? Well, you need to make these early design decisions. You need to do them, make them. If you can't make them, it will not work. How to do that? Well, you need a process. And I know that when I mention process, students fall asleep. But some wise guy once said that if you can't describe what you do as a process, you don't know what you're doing. So it doesn't have to be a big unified process here. It needs to be some kind of structured work with a reasoning framework, with some notations that you can use to create these views to communicate with the stakeholders. And also, of course, for evaluating your options using various approaches. I mentioned at the beginning that, well, you all know how to program, and the thing here is that many of the things we talk about at the architectural level are also important on the implementation level. Remember? Design patterns. You allocated responsibilities to your classes. You allocated responsibilities to your functions. But it's also valid one level up at the organizational level. On the organizational level, we talk about enterprise architecture. And the enterprise architects are responsible for seeing to that systems and infrastructure within an organization works together. You need to make decisions at the organizational level concerning all the systems within that organization. In the same way as you need to make the decisions about a single system before you start to talk about the subsystems of that system. So it's one big hierarchy. So the problems are similar, the principles are similar, and the solutions are similar. So if you know your design patterns, it will be kind of same, a little bit different though. Okay, so that was the first lecture. We have 9 more. I'm not sure if you looked into the My Moodle page. I made it public this morning. Plan is to stream and record and publish recordings of these lectures on the My Moodle page. I have to bear with me that technology is not always on your side, but we will do our best. The examination, there will be 2 assignments and 1 design project. And the first assignment is already up, and it's due next Friday. So I know that many of you just started your degree project, so you have to work overtime the coming 7 days. And on the My Moodle page you will find information about the literature. I often get the question, do I need to buy the book? No, you don't. But I wouldn't have the book on the list if it wasn't useful. But you can find most of the information, if not all, in articles. The guys that wrote the book, they have published themselves heavily, so you will find most of the materials somewhere, but not packaged in that way. So today's takeaway. Software architecture is about decisions. Decision about systems structure and systems behavior at the level that you can communicate to various stakeholders that their concerns are met by the system. Okay, so that was all. A little bit quick today, but I have a doctor's appointment at 3, and the doctor didn't accept lecturing as an excuse. So I'll see you guys next week for a lecture. But keep your eyes open, because I will schedule slots where you can sign up and discuss the assignment with me. Maybe beginning of, well, definitely beginning of next week, maybe even on Friday, but definitely on Monday and Wednesday. So keep your eyes open for that, and I'll see you next week. Okay? Take care.